Hello, everyone. Welcome to Theo-MathProblemSolver. In this particular episode, I'm so excited to take you through the journey of finding absolute extrema values of functions of a closed interval. In our previous episode, we look at the maximum minimum principle 1. But in this particular episode, we are looking at the maximum minimum principle 2, which is interesting, okay? Because we are going to leverage on certain theorem to solve real-world problems. All right, so stay with me even as we explore them together. So at the moment, if you have not subscribed, please do so. Turn on the notification button so that anytime I release new content, you'll be the first to receive them. All right, let's get started. So our first theorem of this particular episode is that if I give you any, function, so let's call the function f, okay? So let me underline some salient points, salient sentences that I believe it's so critical to this theorem. So suppose a function is being given such that the f prime of x, in other words, the first derivative exists for every interval or for every value in the interval I. Okay, all right. And that there exists only one. So let me underline this. There exists only one or exactly one critical value, let's call it C, in that particular interval, for which the first derivative, okay, for which the first derivative being evaluated at critical value is 0. Then we claim that the absolute value, okay, then we claim that a function being evaluated at the absolute value, then the function being evaluated at the critical value is the absolute maximum value over that particular interval, if and only if, okay, if the second derivative being evaluated at the critical value is less than 0, okay, or is negative, okay, it's less than 0 or it's negative, or if the function being evaluated at or the function evaluated at the critical value is the absolute minimum value over the interval if the second derivative being evaluated at critical value is greater than 0 or is positive. Is that okay? So I want us to kind of make sure we understand this theorem so that we can use that to solve problems. Is that okay? So if I give you any function that exists for all values of x in a particular interval, then we claim that if there's only one critical value, okay, then the function evaluated at the critical value is the absolute maximum value over that particular interval if the second derivative evaluated at critical value is negative, okay? Conversely, the function evaluated at the critical value is the absolute minimum value over the interval if the second derivative evaluated at the critical value is positive. Okay, so I want us to please take our time to really understand this, particular theorem so that we can leverage that to solve problems. All right, so at this point, I want us to solve one more example, then we can see how best we can, rely on that to solve other problems as well. All right, so let's dive into some examples. All right. So we are given this particular problem to solve. And with this particular problem, the first thing to do is to find a what? Is to find a critical value, right? So find a critical value. So, but then I want you to pause the video and try it on your own and see how best you can solve this. All right. So I want to point over here. I want to point out that when no interval is specified, we kind of, consider the entire domain of the function. In this case, the domain is a set of all real numbers in this particular, function, because this particular function is a polynomial function. Okay. And the polynomial function is defined for all, the entire, real numbers. Okay, good. So let's take note. So the first thing to do, I would say that the first thing to do is to find the critical values. Okay, is to find the first derivative. Let's find the first derivative. So the first derivative will be what? Will be 4 minus 2x. Okay, and then the second thing to do is to find the critical values. Okay, so find the critical values of the function. Okay, so how do you do that? Since this is just a polynomial, we just set this to 0, which implies that what? We'll have x 4 minus 2x equal to 0. And that implies that my x will be what? Will be 2. So over here, we see is just so, straightforward that we will have only exactly one critical value. Okay, so because we have one critical value, if you are just going to use the maximum minimum principle 2, we are going to use the maximum minimum principle 2 because that's what the theorem says. The theorem says that if you have only one critical value, okay, the theorem says if you have only one critical value, then we should use the theorem. Okay, of which for us, we're so fortunate we just had only one critical value, so we can leverage the theorem. Is that okay? Good. All right, so let's move on. So we can use a maximum minimum principle 2. So what does it say? What does it say? Having realized we have one critical value, what does it say? The theorem says that we should find the second derivative. Okay. So what will be the second derivative of the given function? The second derivative will be what? Will be -2. Is that okay? But it says that we should evaluate it at we evaluate it at the critical value, right? That's a D. So when we evaluate this second derivative at x equal to 2, what do we get? Remember, the second derivative is already constant, so that means we're going to have a -2. But this is what? This is less than 0. If it's less than 0, what did we say? If it's less than 0, what did we say? It means that we're going to have what? The absolute what? Is it maximum or minimum? We're going to have the absolute maximum. So since this particular value, the second derivative evaluated at critical point is less than 0, we're going to have the absolute maximum value. Okay, so we have the absolute maximum value but we need to evaluate it at what? At a function. What did we get if you do that at a function? Remember, the function was giving us what? Let me use a different person over here. Remember that our f of x, which is the function, was what? 4x minus what? X, was it something like that? We're given, yes, 4x minus x squared. Now we evaluate it at what? Negative to the critical value. And that should give us what? And that should give us what? That should give us 4. So which means that our absolute maximum value will be 4, which occurs at where? Which occurs at where? Occurs at x equal to what? -2. So I want us to please take note of that. Sorry, which occurs at sorry, it should rather here, we should rather, because the absolute value was 2, so it's rather 2. I'm sorry. It's not negative, it's rather 2 because I'm sorry. Our absolute value was 2, not -2. It was 2. So let's take note of that. So the absolute maximum value was 4, but it occurs at x equal to 2. So please, let's take note of that. All right. Now, at this point, what will be the absolute minimum? So note that there will not be, so f of x, okay, has no, okay, has no absolute minimum value. Okay, so this will not have absolute minimum value. Okay. In the subsequent examples, I'll explain why we do not have that. Okay, so let's look at. I want us to also take note of something over here. Let me push it down here. So let's take note of something here. It's very interesting. So let's take note of that. So note. Let me do that as a remark. Let me do a different pencil for that. So let me make a remark over here. So I have a remark over here. Now, let's take note of this. If the interval is not closed, such as negative infinity to positive infinity, or 0 to positive infinity, or A to B, these are closed. These are open interval, okay? And that function has only one, okay? And it just so happened that the function has only one, critical value. Then we have to leverage the maximum minimum principle too, right? I believe we are now okay now. We are okay with this. Now, in this case, in such a case, if the function has a maximum value, then it will have no minimum. And if it has a minimum, it will have no maximum. So please, let's take note of that. So please, let's take note of that. If it just so happened that the interval is open and that the function has only one critical value, use maximum minimum principle 2. And we are saying that in such a scenario, if the function has a maximum, then it will not have a minimum. On the other hand, if it has a minimum, it means that it will not have a maximum. So these are something that I want you to, take note of and put that in your pocket. So anytime we encounter problems, then we can go back and use it at our advantage. Is that okay? Very good. Search is so powerful. So I'm taking my time to, really, highlight. All right. So on that note, let's cut some example. So this example, if I were you, I would just pause the video and try to solve it on my own and see. And afterwards, you can compare your result to mine and see what we can do. Is that okay? All right. All right. So let's move on. So let's see how best we can solve such a problem. So we are given this nice function to solve that is defined over the open interval 0 to positive infinity. Now, how do we find the absolute extrema? And as I mentioned, extrema is a collective name for maximum and minimum. So take note of that. All right. So the first thing to do is to find the first derivative. Is that okay? Is to find the first derivative. But if I were you, I would rewrite the function. Because of fractions, I want us to write the function this way. Okay, so that it will be easy to just differentiate instead of using the quotient right away. Okay, good. So our first derivative will be what? Will be 5 minus what? 35 all on what? X to the power 2. Is that okay? Good. Now, since Our first derivative, or f prime of x, exists for all values of x in this open interval. Okay, the only critical values are those for which our first derivative will be 0. Is that okay? Okay. All right. So on that note, we just have to set this to 0. Okay. So we need to set our first derivative to 0. So this implies that 5 minus 35 on x to the power 2 will be 0. That will be set to 0. Then we kind of solve for x. Okay. So with that, you're going to have what? 5x to the power 2 equal to 35. Now we take this, we divide both sides by 5. Then we divide both sides by 5. And that should give us what? X to the power 2 equal to what? 7. Then we take the square root on both sides. In that case, we should have what? We should have what? Plus or minus root of what? 7. But remember that we said that the function was defined over the interval 0 to positive infinity. Okay? But plus or minus 7. So we have to make sure that the critical values should be found within this interval. We realize that remember that the critical values were negative root of 7 and positive root of 7. But we found out that the negative root of 7 it's outside this interval. So in that case, since it is outside this interval, we're going to throw the negative root of 7 away. Okay, we're going to throw that away. So on that note, we're just going to use only x equal to root of 7. Okay. Okay. So we are using this. Okay. Very good. So having noticed this, what do we do? So the C part, what can we say? So we are saying that, see, when you look at the interval is not closed. And that the only critical value that we had was root of 7. And I've explained the rationale behind that. So it just means that we can just use what? The maximum minimum principle 2. Okay? In which case we're going to use the second derivative, right? Very good. So let's move on. So on that note, we're going to find the second derivative. Now, what will be the second derivative of the first derivative? The second derivative will be what? Remember that our first derivative was what? 5 minus 35 on x squared. But if I were you, I would rewrite this as this, okay? Sorry, our first derivative was this one. Then our second derivative would there be what? What would be our second derivative? That should give us what? 70 out of what? On what? X to the power 3. Good, 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 good. Now, remember, we said that we haven't found a second derivative. We evaluate it that way at a critical value. And the critical value was a root of 7. So we're going to have 70 divided by root of 7 or to the power 3, which is what? Positive, right? Since this is positive, what did we say? So it just means that, so therefore, our f of x has what? Has an what? An absolute, is it minimum or maximum? That will be minimum. Good. So we'll have an absolute minimum value at what? X equal to what? Root of 7. But what is the value? What is it corresponding value? What is it corresponding value? Let me just push this downward a bit. All right. So the value will be what? remember that we said that we have to evaluate the main function at critical value, right? And remember that the main function was given as what? F of x was given as what? 5x what? Plus what? 35 for x, right? So we are going to evaluate that. We are going to evaluate the main function at x equal to root of 7. So on that note, you're going to have 5 multiplying root of 7 plus 35 on the root of 7. And that should give us what? So this, you just have to use a calculator. And that I think that should give us 10 root of what? 7, okay? 10 root of 7. So which means that the absolute minimum value is what? 10 root of what? 7. I hope at this point we kind of have a comprehensive understanding of what the maximum minimum principal tool is. So it just point out that if it just so happen a function, it has, it's defined over an open interval, and it just so also happen that it has one critical value. The rule says that, or the theorem says that, use the maximum minimum principal tool. And with that, we're going to go forward to find the second derivative, okay, of the given function. And then what happens is that we're going to evaluate such a second derivative at the critical value. That is not enough. When you are done, then you go back to the main function and then also evaluate it at the critical value. That will help you to do the classification. Is that okay? It's very interesting, and uh, in subsequent episode, we also relate it to real world situations in the semiconductor industry, in the banking industry, in economics, in epidemiology, in the pharmacology. How did they leverage such principles or tools to solve their problems? So in subsequent episode, I do not want you to miss them. Please, if you have not subscribed at this point, please subscribe, turn on the notification buttons, like my comment, and anytime I release new content, you'll be the one to be the first to have them. And also, let's share this content with other colleagues so that we can help demystify the myth around mathematics. Stay blessed, and see you in my next episode. Stay blessed. All right.